Welcome back, everybody. So we're going to be starting up, we're going to be finishing 2.1 and going on to 2.2 today. The exam is coming up on Monday. And it covers all of Unit 1 and then 2.1. In particular, just the definition of the derivative. Yes.
Right, start class.
So it?
Is it right at the start of the class?
Yes, it'll start at the beginning. And as soon as you finish the exam, you are free to go. Classic question that students will ask me is how many questions on the exam? It's not important. The number of questions does not matter. I could make a 2-question exam that is infinitely harder than a 200-question exam. So the number of questions does not matter. What I can tell you and what I can promise you is that I've always designed my exams so that they are doable within the time limit, with ideally enough time for you to go back and check all of your answers. So we have an hour and 50 minutes. I try to make my exams for this class about hour and 30, so you have 20 minutes to check your work. Most students will not take the entire time. That's at least my experience that I've had with the several times that I've taught this class. Taught it now at CSN. I've taught it 10, 11 times, and each time, like, very few people are here until the very, very last minute. And those people who are here at the last minute are usually just checking their answers. They're not trying to do new work unless they get a stroke of genius at the end. I will tell you the exams are usually about, I'd say, anywhere from about 7 to 13 problems, 7 to 14 problems on about 5 to 7 pages. If it's 7 pages, it probably means that there's some problems that just require a big graph or something like that, something that requires a lot of space, but not necessarily a lot of work. Does that make sense? Like maybe it's a question like question 3, and I want to give you a big graph, so that's going to take up a lot of space on the page, but there's not going to be that many questions because half of the page is for the graph. So anyways, as a reminder about it, you will be given an opportunity to get points back after the exam. So you'll turn them in. I will grade them, and I will write very, very little on the exam. I'll either write like check marks and X's. It is your responsibility after the fact to see what you did wrong and try and figure, or more specifically, to try and figure out where you went wrong, and correct the work. You like on the back of the previous page. So people watching the record, well, I mean, I can draw it here. Imagine, so when you open up your page, like if you were to open up your exam and keep it completely splayed open with both pages, it'd look like this, right? They'll be sharing this like that, right? And here's question 1, question 2, question 3, right? And this is the back of the cover page. Right? So that's like if you were to open it up, I want your redo over here. We'll talk more about it after the exam gets handed back. Redo work. That way, when I'm grading the redo, I have both your original work and the work that you did to correct it right on the same page, like right in front of me. So it's much faster for me to grade. If you guys want me to get them back to you faster, please follow this. I'm not going to mark you down for writing like on a wrong spot, but please do it this way. That'll make it a lot easier. But that's how it's going to work. You do not need to redo problems that you got full credit on, and you do not need to redo all the problems you got wrong to get points back. So like if you didn't know how to solve question 5 and you still don't know after the exam, you can skip that problem and still get the redo points from all the other problems that you did. It's not required that you redo the entire exam. It is useful for you, but it is not required to write down where you made mistakes. Like I've had students write that down in the past, and they've said that it has helped them. It's like saying, I forgot to do this, and here's the actual corrected work. But that's just an extra little cherry on top. You can just write the redo of the work. If it's a problem that doesn't really require any work, you can just write the answer. But we'll get to that later on. You can redo it for up to 50% of the points back. So if you got if the question's worth 20 points and you got 10, you can get back up to a 15, and so on and so forth. When I hand it back to you, you have exactly a week to turn it back in. You can turn it in early if you just want to get it out of your hair, but you don't have to. You can wait until the very until class the week later. So ideally, I will hand them back. You'll take it on Monday. I'll hand it back to you on Wednesday, and you'll have until the following Wednesday to turn it in. That way, you have a chance to come to my office hours if you have questions, or email me questions over the weekend. As a real important reminder, the corrections need to be your own work. It needs to be coming directly from your brain and any resource that you can find, whether it be online or offline, but it cannot have a solving component. So that means no photo math, no none of that stuff, no Wolfram Alpha. It needs to come from your brain, and like you can look at notes, you can look at our notes, you can look at Paul's online notes, you can look at practice problems that might help get you the idea, but no help from outside sources other than those types of things. So no tutoring, no parents, no friends, and nothing like that. You can't work together, but the only person you can talk to is me. You can definitely talk to me. Even if you don't know how to start the problem, you can say, I have no clue how to start this problem, and I will usually give you a hint. I'll say like, try and look at unit 1.1, question 5 or something like that. That should help you get started. It's usually best as a helpful tip when it comes to that stuff. If you're stumped on something, or if you have an idea and you're not sure it's right, please send me a picture of your work. That way I can see what you're talking about. One of the problems with emails is it's very, very hard to describe math via email, especially calculus, because like writing limits is a nightmare because you have to like limit, underscore, parentheses, x equal. It's awful. So it's best if you send me a picture of your work. Okay? Any questions on that? Yes. YouTube, no, because that is you actively looking at a video to understand something. Even if the problem so even if it's a problem that's very, very similar, I'm okay with that. Just make sure that you're producing the work from your own understanding of it, right? That's the whole goal of this process, is to make you learn from your mistakes, because that's what math is all about, is learning from mistakes. So, any other questions? Yes.
You say that at most you can get back half of the amount of points that you've got.
That you got, yes. So if you get a 60, you can get up to an 80.
What if you get, like, what if you just got a 0 on the problem? How does that work?
You can get up to 50% of the points back on it. So if you get
with the possible.
yes. So if you get 0 on a 10-point question, you can get up to a 10.
Would it be up to a 5?
What did I say?
10.
Oh, if it's a 10-point problem, you can get up to a 5. I can do basic math, I promise.
Thank you.
You're very welcome. Okay, any other ones? Okay, just testing you guys on your arithmetic, make sure you're paying attention. Okay, one thing, Alyssa found a mistake in our notes. I have a wrong answer key, and I've already updated it, but not for you guys. This should actually say 8 here. The numerator is correct, it's just the denominator was incorrect. I don't know what I was doing, but I forgot. I meant to write. I meant to write 8. So just please make sure you notice that. So
And the negative one's supposed to be a positive one? Is that what you got? Like a negative infinity, comma, 1 minus.
no, you're right. So boom, boom, boom. Thank you for catching it. Now it looks perfect. All right. Thank you for catching that. If you ever find, so I am not infallible. I make mistakes all the time in mathematics. So if you ever catch a mistake or you think there's a mistake, please let me know so I can update it as soon as possible and let you guys know, and also just make sure these things are as perfect as possible. And then that says see solutions for justification. That's supposed to say coming soon. Don't have solutions yet. I'm working on that. But anyways, any questions before we get started for today on Unit 2? So technically speaking, from now on, we are going to be working on material that is not covered on the first exam. The exam will only cover up until 2.1.3. And I promised you I have this. I forgot about it. During the break, I'll write down the solution and we can look at it so you can check your work. But okay. So we'll get started. Example 2.1.6. the derivative of the function f of x equals 1/3 x cubed minus x squared minus 7x plus 2 is f prime of x equals x squared minus 2x minus 7. You can use this without proof, meaning that we don't need to go through and find the definition of the derivative. We don't need to do, because I don't want you to do 1/3 times x plus h cubed. That's way too annoying. What if it was x to the fourth? That'd be way too, that's 4 foilings. I don't want to do that. That's annoying. I mean, I'll do it. It's kind of a fun Friday night activity, but like not very, very useful for class time. So we're gonna assume, or we're gonna just use that as a fact and determine the points where f of x has a tangent line with a slope of 8. Okay, we've never done this before, but when it comes to that type of a problem, if you've never done it before, appeal to what you know, write down what you know. So we know that we need a slope of 8. That means that m sub tan needs to equal 8. But we know that the slope of the tangent line comes from the derivative. The m10 is equal to f prime of a. Or x, but like specifically, I want to say a because we're trying to find a specific value. X is meant to be like a variable that varies like just in general, whereas a is like usually designed to be a specific a value that you're trying to find. But you could write f prime of x. So then we know what f prime is. That means we've got f prime of a is equal to 8 because we've got this kind of string of equalities. So that's to say a squared minus 2a minus 7 is equal to 8. And that's a polynomial equation. We can solve polynomial equations. Polynomial equations are fun. So just need to bring everything to one side. So that's a squared minus 2a minus 15 is equal to 0. And I've made this one, like sometimes the answers are nice, sometimes they're not nice. Please remember the quadratic formula when it comes to the exam. I won't provide it. Does everyone remember the quadratic formula? It's okay if you don't. I will do it one time for you guys right now. All right. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And that is the last time I'll say it. You will never hear me sing it again. Granted, now it is recorded online, so you can listen to it again if you want. I know I have a beautiful voice.
And if you heard it before, it's stuck in your head now for the next 10 minutes.
Indeed, indeed. And that's the song I sing to my son to go to bed. It's an excellent song to sing. He's going to be learning calculus by 3, otherwise, or by 5. Otherwise, I'm going to be disappointed in it. I'm just kidding, Phoenix. If you're ever going to watch these videos, got like 80 million of them now because I'm recording for all my classes. Anyways, so if you don't want to go through and factor it by hand, or if you keep trying to factor by hand and it doesn't work, then use the quadratic formula. But either way, so this actually does factor to, so we're just going to make this really tiny. That over there. This does factor nicely. It factors to a minus 5 times a plus 3 equals 0. That gives us a equals 5 and negative 3. And John Doe student, silly John Doe, he boxes in this as his answer. Why is he wrong? That's just the x value. It's asking for the points. Do I plug it into f prime or do I plug it into f? F, because we're talking about points on the curve, not points on the tangent line, points on the curve. So f of 5 would be 1/3 times 5 cubed minus 5 squared minus 7 times 5 plus 2, which I don't know off the top of my head. If you do, kudos to you. So 1/3 times 125 minus 25 minus 35 plus 2 is negative 49/3. And then f of negative 3 by a similar argument is going to be 1/3 times negative 27 minus 9 plus 21 plus 2 is 5. So the points are then 5 comma negative 49 thirds and negative 3 comma 5. Yes, G.
Because the original f(x) is just ugly to begin with, that's why we just use f prime in the very beginning, or
Nope. We used f prime in the beginning because the slope of the tangent line comes from the derivative. So that's why we set the derivative equal to 8.
All that we get from the derivative, right? Is the slope.
At this current juncture, yes, that's all we can get from the derivative is a function. And when you plug in specific values, you get the slope of the tangent lines at those x values. Later on, we will be able to use the derivative for multiple other things. But for now, that's all we've got. Any other questions? So the last key fact about the definition of the derivative, or just the derivative in general, is that in a physical, and not like exercise, but physical as in physics, and real life sense, the derivative represents the instantaneous rate of change. So, as an example of this, imagine like you can find out your average speed on a road trip. You start your road trip with zero hours into the road trip. It takes you 10 hours to get there. You traveled 500 miles. You're going at an average speed of 50 miles per hour, right? But how does your odometer work? Your odometer is basically doing calculus for you. Not really, but essentially it is. If you want to know your instantaneous rate of change, that's your velocity. So in physics, because physicists are weird, which one do I want to use? That's my notes. There it is. The position of an object at any given time is usually denoted by S of t. We usually denote it S of t. Why? I have no idea. Ask the physicists. They're the ones that call tori donuts. They're dumb. Torus, by the way, is the donut shape. That is called a torus, not a donut. So don't let your physicist, your physics professors tell you it's a donut. It's a torus. And then they'll call this a washer. That's an annulus. So make sure that you get really on people's cases when they're looking at washers and stuff. Actually, that's an annulus. Please make sure you're channeling your inner barista to correct people. So the derivative of the function, the position, is going to be the velocity of the object. The velocity of the object, which is denoted v of t. That's why it bugs me why they named the position function s of t. Why didn't they denote it p of t? P for position, v for velocity, and so on and so forth. You'd think so, but then again, it's a physicist. So burn on physicists. Anyways, so since the v is the derivative, what we have is that v of t is the derivative, is s prime of t. So that's just an important little aspect about physics. We don't do too many application problems in this class, at least in my opinion, because that's what physics is for. That's what they're going to be testing you on. I don't need to retest you on physics, especially since physics will find different ways that are more clever to figure out these problems. I remember I was teaching a calculus course, and a bunch of my students were taking AP physics, and I put on there, because it was required by the school, I put on the exam a problem involving a spring and calculating work. And I was expecting them to do it the math way, but they had learned something in physics that had done it way differently. So I thought they were all cheating. It's like, no, this is way easier to do with something in physics, something Hooke's law. I don't know. So we won't do too many word problems, but every once in a while we'll throw them in there. But we'll do that later on, because I want to focus more on the derivative as a concept And calculating derivatives is tedious enough without having to do more real life sense on top of it. We'll learn how to take derivatives quickly soon enough. So differentiability. So we say that a function f of x, we say that it is differentiable at x equals a if f prime of a exists. I know I gave you plenty of room to write that, so squeeze it in there. And by the way, the abbreviation for differentiable, how do you spell abbreviation? There you go. Is DIFF''BLE. So sometimes I'll say diffable, meaning differentiable, because I don't like writing that all out. But we say that a function is differentiable at x equals a if the derivative exists there. Just like you're continuous if you have that condition, you're differentiable if you have that it exists at that value. And you're a differentiable on an interval if you're differentiable at all the a values in your interval. And if your derivative is defined everywhere, then you are differentiable everywhere. So some pictorial representations of non-differentiability. So I'm going to show, I want you to draw 3 graphs here. You don't need to worry about scaling. But then mark a point A there. And then I'm just going to be super awesome and be able to recreate it. And then for the corners and cusps, I want you to do 2 graphs. And then for a vertical tangent line, I want you to do just 1. So I'm going to wait for a second for you to draw all those things. If I really cared, I'd put those in there for you guys already. I'm saying that as a joke. I should do that. I just hadn't thought about it until now. So maybe I'll, you know what? I'm going to add that while you're doing this. I'm going to add that into my note of a million notes. What the differentiability? Add diffability page. Okay. You don't think it saves you a couple, okay? It saves you a couple letters. Remember, we're all worried about carpal tunnel. Every single letter helps, okay? You want to be able to play Dota or League of Legends for as long as possible. And when you're 80 years old, you got to be playing. Yeah, exactly. It's you live on toxicity. It's great. It's great for our bodies.
Like yourself.
Nah, you're having fun. Okay, so some discontinuities. So discontinuities cause differentiability issues. So one situation would be something like this. This function is differentiable everywhere except at a. And I'll explain why in just a moment. Another such example would be something like that. With or without a point, doesn't matter. And then also, remember, we have infinite discontinuities. So it could be something like this. Something like that. And so how do we know that it's not differentiable? The first two, you can, the first and the third make sense visually. Because think about it this way, and so people watching the recording online, sadly, you can't see this because I'm gonna have to, and I'm tall, but I'm not that tall. So tangent lines. If you were to try and draw a tangent line at A, on one side you're looking like this, and on the other side you're looking like this. In order for the derivative to exist, the limit needs to be same on both sides. If you make h go to 0 from the left, your tangent lines will be approaching like that. Whereas if you're approaching from the right, your tangent lines will be approaching like that. And so they won't give me the same number. This one, the problem is, yes, it does look like there's a tangent line there, but think about how the definition of the derivative is defined. The derivative, specifically the secondary format, right here, this version of it, or more specifically, since we're looking at a specific value right here, f of a is not on the curve. So it's way up above it. So if I'm trying to, come on, there we go. If I'm trying to create the definition of the derivative, then I'm using this solid dot to try and find tangent lines, and that won't work. And the third one, once again, if I try and draw a tangent line, I end up going up and towards infinity on the left, and then my tangent line here is kind of slanted like that, and they don't agree on either side. In order for us to be differentiable, you'd need to be able to draw a tangent line there. Corners and cusps. So the first one I'm going to do as a corner. And then a cusp. So a corner is exactly what it sounds like. So it'd be something like this. That's the issue. That's the corner. And once again, if you try and draw a tangent line, by the way, which is easier to see? Is green or red? Easy to see on it. Green. Okay. So if you were to try and draw a tangent line, on one side of A, you've got a positive sloped tangent line, but on the other side of A, I'm not happy about that. No, I didn't read that as well. Nope. There we go. On the other side of A, you've got a negative sloped tangent line. So the left and the right-hand limits will not agree there, which means that the full limit does not exist, meaning that the derivative does not exist there. And a cusp is a very, very interesting thing. A cusp looks like this. That's a cusp. And so you'll see that it approaches infinity on either side. One side starts to approach positive infinity, and on the right-hand side it starts to approach negative infinity for the slopes of those tangent lines. And infinity is not a number, so the derivative does not exist there. Like we could say that f prime of a would be positive infinity or something like that, or negative infinity from the right-hand side, but ultimately, if something equals infinity, it doesn't exist. It's more of a concept. Any questions on that? Yes.
So the cusp requires that they go to infinity, so if they ended at points, it would be defined as a cusp.
Say that one more time.
If they ended at points, like instead of the arrows, they ended at some fixed value, it would not be considered a cusp, even if it was the same shape.
I'm not quite sure I understand. Sorry, one more time.
Like, so it comes to that point, but I think you're saying that because the left approaches negative infinity and the right approaches infinity is what defines the cusp? Is that not right?
Yeah. Darn it. So the cusp, like if we're examining it really, really closely, hopefully I'm clarifying and I'll answer your question with that. So your tangent lines, positive, more positive, more positive, more positive, and then basically vertical, undefined slope. But it's coming from positive slopes, and then on the other side, it's still vertical, but then it starts going towards negative infinity, or like it starts becoming negative.
Okay, my bad. It was the tangent line you're referring to. So if these ended at points, that would still be the case because, like, if the graph was finite on the left and finite on the right, the tangent line still approaching infinity.
Yeah, at that specific value.
Okay, I see.
Okay. No, thank you for asking for clarification. And then the last one, these are the hardest cases to see, specifically if you're just graphing it on like Desmos or something, but they look something along the lines of this. like cubed root functions. They are not differentiable at 0. A cubed root function is not differentiable at 0 because you have a vertical tangent line. So yes, you can draw the tangent line, but it's a vertical tangent line, which means that it has an undefined slope. Let me say that one more time once you're finished writing, because this is an important understanding. The tangent line does exist, but f prime of a doesn't exist because f prime of a is the slope of that line, and the slope of that line is undefined. These vertical lines have an undefined slope. Any questions on that? Next thing is a theorem, like an important little thing that says, if your function is differentiable, then it is automatically continuous. So if you know you're differentiable, you're automatically continuous. Note the reverse. The reverse is not true. If I want to bust out some philosophy of logic terminology, I would say the converse, not like the shoe, but this. So the reverse is not true. Continuity does not imply differentiability.
So a vertical tangent line would be an example of that, right?
Yep, that vertical tangent line is a perfect example. That function is continuous everywhere, but it is not differentiable at A. Differentiable everywhere else, but just not at A. So that's just an important distinction. Is like it is a useful fact later on in mathematics. It's not super useful for us. Just suffice it to say that if you know that you're not if you're not continuous, so the main use of this theorem, if not continuous, not differentiable. So if you're not continuous, you're automatically not differentiable, as we saw in the previous situation. That's the main use. And that, by the way, is what we call the contrapositive. So that's flipping the if-then statement and then negating those statements. Just as a fun thing. If you haven't taken philosophy of logic, I highly recommend it. It's a very fun course. Working about logical arguments and then working with symbolic logic. It's very, very fun. Very fun. And you learn about contrapositives, converses, and how the truth of those things works out. If your full statement is true, your converse isn't necessarily, but the contrapositive is true. Very, very fun stuff. Highly recommend. Anyways, in the interest of time, I'm going to skip these two problems, this one and the next one. I might make a video on the two of them, but we're not going to go over them in class unless we have extra time, which I doubt we will. So just ignore those ones for now. We'll go on to this problem here. The graph of f is given below. Answer the following questions. Where is f discontinuous? Always looking for the moving left to right. What's the first discontinuity? Yep, x equals -4. Once again, this was before I was able to, before I was good with Desmos. And because this function took a long time to create, I don't remember how I made it. So I think this was using a tangent line, tangent function, and this was a circle, and this is a line, and this is a line. And I don't remember, this is an asymptotic function. But anyways, x equals -4 is one of them, yes. Then what? -1 is a point of continuity, but it's not differentiable. And then +5. And those appear to be the only values. And let's just add arrows to make sure it's very clear. So those are the only 3 points of discontinuity. Then it says, where is it non-differentiable? Well, because it's discontinuous at -4, 2, and 5, we know those are values of non-differentiability. So x equals -4, 2, and 5, and we're going to say because discontinuous there, discont there. But then we also have a few more. Now the graph is hidden right now, so I'll let you write that down. But if you've not finished, don't worry, I'm coming right back to it. So we're looking for discontinuities, which we already found. And so we're looking for corners and cusps and infinite tangent lines. -4 was already taken care of, even though it'll be like infinite tangent lines. Then -1, as Alyssa suggested, is a cusp. So -1. We can write a cusp. And then there's one other one. 9, because that is a corner. And those are our values of non-differentiability.
Can you talk about this for a second?
Yes.
Why, that x equals -7, why that curve is not, or why that is differentiable?
At -7?
Yeah.
So, excellent question. Actually, that's going to be one of the questions we're going to ask next. So, find the values of f prime of -7, unless there's any other questions on part B. Yes. 9 was a corner. Yes, thank you. Just so thank you for bringing that up, because I wanted to mention, I don't require, just like I don't require you to define what type of a discontinuity it is. You don't need to say it's a jump discontinuity or an infinite discontinuity. You don't need to specify that it's a cusp. It's just for our notes purposes. On an exam, if I said, where is it non-differentiable, you could just say the values and be good with it. Okay? Find the value of f prime of -7 and f prime of 8. Okay. I'm going to underline these. Let's use green and pink. I'm going to tell you that f prime of -7 is equal to 0. And I want you to look at this and think about why. Why do I know that immediately without even having the equation? Because if I had the equation of this thing, I could take its derivative and call it good. And I can try and plug in -7 and call it good. But I don't. Why do I know that the answer to that f prime of -7 is 0?
It's flat.
The tangent line is flat there. Yes, Louis is absolutely correct. So remember, so key, f prime of A represents the slope of the tangent line at x equals A. That's the key fact that we need to memorize, that we need to know. F prime of A, when you plug in a specific value into the derivative, you get the slope of the tangent line at that point on the curve of F, the curve of the curve F. So, looking at it, don't worry if you don't have that listed. I will take care of it in a second. There's the point on our curve, F, and then if I were to draw a tangent line through there, it would be 0. Slope equals 0, which implies the f prime of -7 is equal to 0. Any questions on that?
And that's just because it's just a straight line.
Yes, just a flat horizontal line, and horizontal lines have a slope of 0. They have 0 rise over infinite run. Over any run, I should say. And then it says find f prime of 8. So I'd like you to look at this and tell me what you think it is. So 8 is right there. And if I were to draw a tangent line, it would actually end up being the exact same thing as the line itself. And the slope of this line is 2. Now, luckily for us, this is one where you can just, because we got the grid lines, we can go rise is 2 over a run of 1, or a rise of 4 over a run of 4, or a run of 2. But if you don't have the points, or if they're really, really awkwardly placed, you can always use the slope formula, right? Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. but usually you'll be able to find it nice and neat enough. That implies that f prime of 8 is equal to 2. Any questions on that? I can zoom out so you can see everything since that's the limitation of the notes here is that I can't put the whole page on there without it becoming super small.
You can say limits of notes without purpose.
Say what?
It's a-
Limits of the, oh, the limits of the notes, yes. We have our limits. Wow. You've probably heard this joke already, but once again, now you can really understand it, is that calculus teachers, they never drink because they know their limits. So, or the better version is know your limits, don't drink and derive.
Yeah.
So great joke. But anywho, so that is the end of 2.1. And once again, so if you're I posted the exam review. If you didn't already check the homepage, it's right on the front page, but it's all like you can scroll down and look at exam reviews. And once you click on that link, it will bring you to the exam review module. Exam 1 review is there along with the solutions. As I said before, please attempt the problems yourself first. If you get it right, kudos, you got it, you understand it. If you get it wrong, look at the answer key on the original review problems. The answer key is on the review problems at the very end of it, and try and figure out where you made a mistake. If you really can't figure out, then that's when you do the solution guide. And look at the solution guide to figure out how you did it. Then my recommendation is try a problem of similar difficulty. Try a problem that's similar from the notes or from Paul's online notes or anything like that. Try and find another problem to practice. So that would be my recommendation. However, I mentioned it on the homepage and everything. The unit 1, I'm making a change to how I do exam 1. I've tried to change it this semester where I'm including 2.1 on exam 1. So my exam review that I've written for 181, it doesn't have anything on 2.1. So for studying unit 2.1, please look at questions. I'd say question 1, basically. Question 1, if you can do all of those, you'll be prepared for the 2.1 section of the exam. Okay?
Question.
Yes.
About when we have exercises that have trig functions in them,
Mhm.
is it usually gonna be like a general concept as opposed to something where we'll need like the unit circle? Because I get paranoid about that, where it's like, do I need to know that this is, corresponding to -2 over 2 or something?
Mhm.
Or is it just an idea of, what the limit of each, whatever?
You will occasionally need to know your unit circle, but I can teach you a little nifty hand trick.
You know, the sign, is that what you're talking about?
Where like you've got a hand like this. I'll draw it during the break, but 0 degrees is your pinky, 30 degrees, 45, 60, and 90, and you can take the square root of your hand. It's very, very nifty. I'll draw it in a second when we get to a break. Should probably be taking a break very shortly, actually. In fact, why don't we take a break right now? That's a good time for it. Let's come back at 12. I want to do a 5-minute break. So 12:15. So I'll write that thing in just a moment. I'm going to go finish that one problem for us. Where was it? Right here. Oh, people watching the recording, go ahead and do some guided yoga. Again. So we talked about it during the break. If you're watching the recording and you want to know more about what this is, please feel free to talk to me. Otherwise, just assume that it's a bad turkey design. Way back when. And as promised, here is the answer to that example 2.1.3. If you're watching the recording, please pause the video and record it or whatever. Here, feel free to take a picture if you want it. I'm going to move away from it in 10 seconds. To save on time. All right. Now we move on to You might be thinking to yourself, man, is that really what we have to do every single time we take a derivative? Do we really have to do all of that? No. Luckily for us, mathematicians were like, I'm way too lazy to do that. That's one of the things that that's very, very silly about mathematicians. We were very, very lazy. Case in point, we write 3x, but why don't we write 1x? Because we're lazy. Like technically speaking, yes, one multiplied to anything is not there, but like it doesn't matter. But we don't write 1x. We just write x when we're there's another example is very, very common. I can't think of it off the top of my head. Yeah, any integer over 1, we just skip it. So there's a lot of rules that we do as mathematicians that we're very lazy about. We just skip it. We don't want to bother writing it because it's unnecessary. And so mathematicians really thought about things and said, well, we've got to find a better way to do things. And so we came up with some rules. And all of these have proofs on them. There's a reason why they all work. If you want to see the proof of them, I'm happy to show you. But I don't want to waste time during class doing it. So there's the constant or linear rule. Really just call it the constant rule. It says that d dx of c is equal to 0 for any constant. So as an example, d dx of 5 is just equal to 0. Exactly right. You can think of it, you can prove this to yourself either visually with a graph, because any constant function is just a flat line, as Louis suggested. And so if you're trying to look at a flat line, the slope of that line is always 0. No matter what point you pick on it, the slope of the tangent lines will always be 0, hence why the derivative of it. I realized I didn't really talk about this notation, d dx of parentheses. d dx is an operation. So dy dx is a derivative. dy dx is a derivative. d dx is the process of taking the derivative. Does that make sense? So when I write d dx, I'm saying take the derivative of this. We call this an operator in mathematics. So addition is an operator, but we usually write the addition symbol in the middle of it. But point being is d dx is taking the derivative. It's the process of taking the derivative on the inside, whereas dy dx is a derivative. So just make sure that'll play a role when we talk about implicit differentiation in 2.5. But anyways, the derivative of any constant is always 0. And you can also prove it algebraically, because if f of x, just as an aside, f of x equaling c, then f of x plus h is also c, because there's no x to plug in. So the numerator of the derivative definition is just c minus c, which is 0. So it just goes away. But anywho, we don't need to spend too much time talking about those things. But once again, if you want to see the proofs, feel free to talk to me. Then we have the power rule, the most important rule. Honestly, this one is central to you need to practice this before we get to 2.3. So we won't be going over 2.3 until Wednesday. So don't bother practicing this until after the exam. But once the exam's over, start practicing the power rule and stuff. So the power rule says that d dx of x to the a is equal to a times x to the a minus 1 for any a. For any number a, for any constant a. So for example, the derivative, so d dx of x to the 7th is 7x to the 6th. Put the number out front and then reduce the power by 1. This only works for constants though. You'll see later on, we'll talk about the function y equals x to the x. The power rule does not apply here because the exponent is a variable and not a constant. So if you see this, you have to do it a different way. And we'll talk about that once we get there. We won't see that for until 2.5 at the earliest. So the derivative of any power of x, where the power is a finite number, put the power out front, multiply it into the x, and then reduce the power by 1. That is the power rule. Then we have the constant multiple rule that says the derivative d dx of c times f of x is c times f prime of x, meaning that you can pull the constant out front. The constant does not affect anything. It does, but it doesn't affect the calculation. Yes.
So the DDX you said is the process of finding the derivative, so like on the power rule, you're saying the process equals 7x to the 6th, or would that be dVdx?
So what this is saying is the derivative of x to the 7th is equal to 7x to the 6th. That's what it's saying. So this, imagine this is saying like taking the square root of something. This is saying take the derivative of the inside.
Okay.
Is that all right?
So then we wouldn't say dVdx equals 7x to the 6th?
No, because ddx would be, so ddx would be very, very dumb. If anybody labels their function as lowercase d, they're being an ass. So ddx would mean taking the derivative of d. But that'd be the derivative of d's, just like dy dx is the derivative of y. ddx would be the derivative of d.
Oh, and I think that's what I meant. I thought that it would be y over dx equals 7x to the 6th. That's why though, because that's a y.
Yes.
We're talking about x.
So
I see.
excellent point. This is important for notational purposes and understanding how we talk about calculus. I say that the derivative of x to the 7th is 7x to the 6th, which is the same as saying dy dx is equal to 7x to the 6th, where this is my y. That's my y. Does that make sense?
Yeah, that's what
So dy dx is the function, it's the derivative. ddx is the process of taking the derivative. When I write ddx, I'm saying take the derivative of this expression. Or more specifically, this function. So they changed notability and it makes it so that you, once you erase once, it switches you back to a pen, which is really frustrating. But anyways, constant multiple rule means that you can pull out constants. Don't worry about them until the very end. Just multiply them in once you're done with everything. And then the sum or difference rule, also called linearity, is that the derivative, so ddx of two functions, f of x plus or minus g of x, is equal to f prime of x plus or minus g prime of x, which means that you can take care of the derivatives separately and then add and subtract them as you need. So you don't need to worry about trying to find the derivative of the whole thing all at once. You can look at each piece. Now the question then, and which I'm really glad you asked it, Brandon, is does this work for multiplication and division? And the answer is no. There are two rules. There's the product rule and the quotient rule, which we'll get to at 2.3. So excellent question, Brandon. I'm glad we mentioned that. The sum and difference rule says that you can split it apart and everything's all fine and gravy. So let's look at some examples. Now we're going to do this in painstaking detail for the first couple times. Once you start seeing the pattern, please skip this step. I want you to skip this. It's way it's just adding more and more chances for you to accidentally make a smudge mark and mess it up. But when we first start off with this is where you go. So f prime of x is going to, I should probably add this at the very top. So let's say d dx of blank and blank prime mean take the derivative of the blue box. I'm going to put a blue box in here. So if I write d dx of something, that means take the derivative, or if I write something and then I write a prime symbol, that also means take the derivative. Some books use it in one way or the other, so I want you to be comfortable with either notation. I typically use d dx, but sometimes it makes it a lot like writing d dx is a lot more time consuming than parenthesis prime. That's only 3 pen strokes as opposed to 1, 2, 3, 4. So you save yourself on one pen stroke, but you're also having to write a D, which is way harder than writing a parenthesis. Either way. So f prime of x, you're going to take the derivative of each piece separately. Because imagine trying to find this by the definition. You'd have to do 3 times x plus h to the fourth minus 5 times x plus h to the third plus x plus h squared minus 2 times x plus h plus 4. And I don't want to FOIL out 4 times. That seems way too tedious. And mathematicians agreed. So this is the same thing. When I take the derivative, this will be 3x to the fourth derivative minus 5x cubed derivative plus x squared derivative minus 2x derivative plus 4 derivative. So I'm writing this in painstaking detail, which honestly sometimes makes it more confusing. The more you practice it, the better you get at it. So practice it early, practice it often. So if I were you, since this is not covered on the exam, I might skip this for now. So my recommendation has always been to, once you finish class, try at least once later on today to practice a few problems or go over it again so it sticks in your head better. But since this is not relevant for the exam, spend more time studying for the exam. Then on Monday night, rewatch this video a little bit, do some practice just to refresh it on your mind. But anyways, so the constant multiple rule says that the 3, the 5, and the 2 don't matter. So this becomes 3 times 4x cubed. The derivative of x to the fourth would be 4x to the 4 minus 1 over 4x cubed. Minus 5 times 3x squared. Plus 2x to the first power. What's the derivative of 2x? I'm going to tell you it's minus 2. And then plus 0 for the derivative of 4. The reason for that, d dx of 2x is really d dx of 2x to the first power. So by the power rule, this would be 2 times 1x to the 1 minus 1, 2x to the 0, but anything raised to the 0 is 1. That's the reason why. So there is technically, there might be a rule, like an additional side rule that says the derivative of, like we can even make this a rule if you want. So d dx of a times x is equal to a for any a. For any a, not all. So that's an additional rule that if you want to memorize it, but you can also just realize that it's power rule in action.
It's like the outcome of the product rule.
The power rule.
Oh, yeah, sorry.
No worries. There's going to be another P rule, the product rule later on. So simplifying this out, that means that f prime of x is equal to 12x cubed minus 15x squared plus 2x minus 2. That is our derivative. Any questions on that? Okay. Next one. And so if you feel comfortable, and I encourage you to get good with the mental math, so I'll do it for the people watching recording. Basically, go 4 times 3, that's 12x to the third power. 5 times 3, 15x to the second power, because you reduce the power by 1. 2 times 1, x to the first power, and then Derivative of 2x is negative, negative 2x is negative 2, and so on and so forth. I'd like you to get to that spot sooner rather than later, as soon as possible. Start skipping this algebra, because doing this every single time is just time consuming. It's a guaranteed way to increase the possibility of making a mistake. So, yes.
You want me to find the derivative of?
Constant rule. Very first one, it's not up there right now, but the derivative of any constant is 0. Next one, g of t is equal to the third root of t plus the fifth root of t squared. Oh no, we don't have a rule about radicals. There was no rule about radicals. So you gave us an unsolvable problem. That's not possible. Yes, it is. Remember, you can convert to exponential form. First, convert to exponential form. G of t is t to the powers above us, roots below us, right? So t to the 1/3 plus t to the 2/5. I know fractions. I know they're not our best mates. I know we don't like them usually. I don't know why. Maybe they make it hard to close up shop, when you're trying to close up for the night at Starbucks and you want to get out at 11, but the person you work with is a chatterbox. Loved LG. She was a nice shift soup, but she talked way too much. And I had to take a 5 a.m. shift the next day. So kind of on my S list, if you know what I mean. Anyways, so G prime of t. This is the way I would like you to work with it. So this would be 1/3. Remember, this works for any number, any finite number. You can take the derivative of it with the power rule. So this would be 1/3 t to the negative 2/3 plus 2/5 t to the negative 3/5. And that's our answer. Now let's think about why. Now, if you're okay doing the mental math, awesome. I'll show you how to do it. So the reason, the derivative of t to the 1/3 would be 1/3 t to the 1/3 minus 1. And the key trick is that when you're subtracting by 1, you can just rewrite it as the denominator number over the denominator number. So you can rewrite 1 as 3/3. 1/3 minus 3/3, that's negative 2/3. It's always going to be, so if it was like for the other one, 2/5, it's going to be 2/5 minus 5/5, hence negative 3/5. If it was, let's just do an obscene example just to drive the point home. The derivative of t to the 99 over 101 is going to equal 99 over 101 t to the negative 2 over 101. You see how that works? That always happens because every single time you do a power rule, you're always just subtracting 1. So please get comfortable with that fractional stuff. It happens a lot more often than you think. So, and also if you really don't want to do it, if you're really like, nah, Phil, I don't need fractions. Fractions aren't important to me. You can always use your calculator. Just put 1/3 minus 1 in your calculator. You're all good. But I like you to get good with the math, the mental math. Okay. Next one, unless there's any questions on those. Find the derivative of h of z is equal to z squared minus 3z plus 1 times z cubed minus 1. Note, d dx, or actually let's write this in shorthand notation. F of x times g of x derivative is not equal to f prime of x times g prime of x. It's not true. We wish it was, right? We wish it was. That would make math a lot easier. It would make calculus a lot easier if that was true, but sadly it's not. Speaking of which, if you have ever heard of the person 3 Blue 1 Brown, he's a mathematician on YouTube. He's brilliant. He's a really cool guy. He does videos on a bunch of mathematical topics, upper division and lower division. He has a calculus series that tries to approach calculus from a visual perspective. And the visual perspective of the product rule is actually pretty cool. So if you want to know a more intuition, like a visual interpretation of why this is not true, feel free to check that out. 3 Blue 1 Brown. Very, very bright mathematician, very, very cool videos. So anyways, with this one, because they're being multiplied together, we can't just find each one separately. We have to FOIL. So simplify first. First, simplify. Later on, we will be able to calculate it by not simplification. We can do it by the product rule, but we haven't gotten that yet. So h of z will then be, okay, so z to the 5th minus z squared minus 3z to the 4th plus 3z plus z cubed minus 1, right? When I distribute that in, so z to the 5th minus z cubed, or z squared, excuse me, minus 3z to the 4th plus 3z plus z cubed minus 1. Okay. And then combining like terms, h of z is equal to z to the 5th minus 3z to the 4th plus z cubed minus z squared plus 3z minus 1. That's just the algebra. I know we don't want to do it, but we got to do the algebra every once in a while. Got to get your hands dirty. Now that we've got it in a format that we can take the derivative of, now we can go through there. So h prime of z. The derivative of z to the 5th would be 5z to the 4th. The derivative of 3z to the 4th would be 12z cubed. Derivative of z cubed would be 3z squared. Derivative of z squared would be minus 2z. Well, minus z squared. The derivative of minus z squared would be minus 2z. Derivative of 3z would be 3. And the derivative of negative 1 would be 0, so I just won't write it. You can write it down if you want to, but it's unnecessary because adding 0, subtracting 0 doesn't do anything. And that is our answer. Any questions on that? Yes.
For negative 3z to the 4, you just multiply 4 times 3, then 4 minus 1.
Exactly right. So yes, for this term right here, the derivative of that one, 3 times the exponent, so that's where the 12 comes from, and then I reduce the power by 1 by using the power rule. Just as a small note, because I want to talk about the power rule one more second. Proving it for integer for whole numbers, so the derivative of the fact that the derivative of z squared is 2z, derivative of z cubed is 3z squared, and so forth. Proving that, not too terrible. Proving it for integers, not too terrible, because you have to use the binomial theorem. You guys remember that? You guys remember? Oh man, I love writing it out, but x plus. You guys remember this rule? You guys remember that? Yeah, it's the binomial theorem, and that's the binomial coefficient. You have to bust that out to do the proof of it. So it's quite tedious, but it's not too hard to do. Proving it for negative numbers, also not too terrible. Proving it for rational numbers, significantly harder. Proving it for irrational numbers, even harder. That is where the bulk of the difficulty comes from, is trying to prove that power rule works for any real number, including pi, square root 2, and so on and so forth. That's where the real nitty-gritty detail comes into play. But anyways, I am getting sidetracked. This one, Same thing is true for division. Note d dx. Well, let's use the shorthand notation. F of x divided by g of x derivative of f over g is not equal to f prime of x over g of x, g prime of x. That's not true. Sadly, we cannot do that. It would make math a lot easier if that was the case, but it's not. There's a rule called L'Hopital's rule, which involves limits and derivatives, in which case that is something that happens, but we don't talk about. Some teachers will teach L'Hopital's rule in 181, but I believe UNLV still keeps it in 182. That's why I'll keep it in 182. But this one, luckily for us, it's just a monomial. Just a monomial in the denominator, so you can just divide it into each thing separately. So simplify. Then f of x will be x cubed divided by x minus 2x to the 1/2 over x, which is x squared minus 2x to the negative 1/2. All right. And so that would be, so f prime of x would therefore be 2x minus 2 times negative 1/2, so plus x to the negative 3/2. Take a second to make sure you understand where that came from. I will explain it in just a moment. Hopefully you can see right away, and if not, it's okay. This is your first time seeing this. I wouldn't expect you to memorize it off right off the bat. Yes. Yes, excellent point. I don't believe in that rule where you have to write your answers in positive exponents. That's a BS rule. That's just making you try and do something that's unnecessary in mathematics. That's that old relic of when we didn't have calculators and teachers still don't want to deal with it. You can write it as a negative exponent. In my class, that's fine. Excellent point. This last one, w to the 7/3 plus 1 over w to the pi. So we didn't have a rule about 1 over w to the pi, but remember this is the same thing as w to the negative pi. Remember, if you have 1 over x to the a, that's equal to x to the negative a. The rule, 1 over x to the a is equal to x to the negative a. Vice versa. That rule, remember, that's true backwards and forwards. So if you have an negative exponent, you can convert it to a positive by writing 1 over. That will be useful in unit 3, but not right now. My rule of thumb, remember, by the way, if you need to use your answer for something, simplify it. If you don't need to use it for anything, like if you're just finding the derivative, keep it unsimplified. Like, don't worry about simplification unless you need to use it for something. So P prime of W is going to be 7/3 W to the, take a second, 4/3. Yes, 4/3. And then the derivative of W to the negative pi would be negative pi times W to the negative pi minus 1. Yeah, it's a weird exponent, but it's just an exponent. It's a number just like you and me. We don't need to be afraid of it. We're all irrational sometimes, right? So it's a weird exponent, but that's the exponent, negative pi minus 1. Please don't write the approximation. Leave it in exact form. So don't write negative 4.14159. Don't write that. Just write negative pi minus 1. Cool? All right. Now you might be thinking to yourself, though, Phil, like, yeah, these are great, but what about all the other functions that we know about? What about e? What about cosine? What about sine? What about tangent? What are their derivatives? And that's a great question. I'm glad you asked it. There are rules for the exponential functions and the logarithmic functions. The derivative of e, best derivative in the world. Best derivative in the world. Derivative of e to the x is e to the x. The proof of that is quite fascinating. This one is a little harder to prove. There's a visual understanding and then there's something else. But the derivative of e to the x is itself. It's the only function that does that besides zero. The derivative of zero is zero. But the only two functions that have their derivative equal to themselves are e and zero. Pretty unique. And that's why I like, so everyone likes to celebrate Pi Day. Pi Day is so cool. It's March 14th. Pi is chump change in comparison to e. E is one of the most important numbers in all of existence, and it's way cooler. But anyways, derivative of e is e to the x. The derivative of a to the x for any base other than that is natural log of a times a to the x. Why is a good question. It's more of a tedious answer, but it has to do with the change of base formula. Well, not the change of base formula. It requires you in a little nifty trick and knowing the chain rule, which we don't have yet. The derivative of natural log of x is 1 over x. And the derivative of log base b for any base, whether it be log base 10, so log, or log base 3/2, is going to be 1 over ln of b times 1 over x. Or if you want to make it look prettier, x times ln of b. If you want it pretty. The proof of that one is very, very cute with the change of base theorem. Does anyone remember the change of base theorem? No? It's okay. It's the dumbest theorem in all of mathematics. That's not true. But it's one of them. It was so cool back in the day, back when we didn't have calculators, but now it's completely moot. Anyways, those are the next ones. I will tell you definitively, don't need to memorize. B and D. A and C definitely need to be memorized. I have been studying mathematics since college. I've been studying for over 15 years at this point, and I've been teaching it for 8 years now. I can count on 0 hands the number of times I've seen a problem in a real world situation or on an exam that really requires you to know those derivatives. So I never put them on my exams. If I do, I will give you that derivative. You don't have to memorize it. Just memorize A and C. All right. That'll do it for today. If you guys have any questions, feel free to email me. I'll be trying to check out my emails over the weekend a little bit more frequently, since you guys have an exam on Monday. Otherwise, happy studying. Have a great rest of your day and a great weekend. And I will see you guys on Monday for the exam. See you then.